9-3 Gibbs free energy. Are you? Yeah, this is exciting times, guys. This is another thing that you get to memorize. This chart right here. Okay. We're going to come back to this if they don't have it down further below. I don't remember if they do or not. So Gibbs free energy describes the energy available in a system that can be used to do work. By calculating this, you can determine if the system has enough energy to undergo the process and thereby determine if the reaction will take place. So, for example, if I had this reaction that I wanted to take place where I am melting water, right? If I did this at minus 10 degrees Celsius, would this happen under normal pressure? No. Okay. If I did this and I changed the temperature, would this reaction happen? Yes. So this is a thermodynamically favorable reaction when we are at 10 degrees. We modify that temperature and we drop it down to minus 10 degrees. It's not going to happen. Okay, so that's what they mean by being thermodynamically favorable. You want to use this terminology, thermodynamically favorable. That is the terminology that you want to use. Come on, you can do this. There we go. That is the terminology that you want to use for this section. Okay. You do not want to use the word spontaneous. They do not like the word spontaneous. Okay. What does the word spontaneous mean to you? That it what time frame? Quickly, right. Okay. And some of these things that are thermodynamically favorable don't happen quickly. Okay. For example, the rust that forms on my truck outside is a thermodynamically favorable reaction. Okay. My truck's like 12, 13 years old. Okay. I guess it's 13 now. So I got a 13-year-old truck out there. Okay. It's got some rust on it. That just didn't happen quickly. Okay. But it was thermodynamically favorable. So that's why they like you to avoid the term spontaneous, because these things don't happen instantaneously. They don't happen, just a snap of the fingers. Some of them are thermodynamically favorable, but they don't happen quickly. So they used to use this term spontaneous, but they don't like that anymore. They want you to not use that. So get this term in your brain. This is what they want when you're writing it out, because this is commonly a lot of times something that you'll see on an FRQ that you have to be able to justify if the reaction will happen or not. And you have to say if it's thermodynamically favorable or not. All right. So we have two forces at play. We have enthalpy, which is your heat, and we have entropy, which is the number of microstates. Sometimes people refer to that as disorder, but they like you to use microstates more. Okay. Back when they were teaching us this, disorder was kind of the common term, but they've kind of shifted away from that. Okay. So they're trying to see if that reaction will happen, and you have to account for both of those. So if a reaction is thermodynamically favorable, we know that it will take place. However, it doesn't tell us how fast it's going to happen. For example, like I said, some thermodynamically favorable reactions are very slow, like the rust of iron. This is an example of a reaction that is said to be under kinetic control. So we have to look at the kinetics of it. So this unit brings together a lot of different sections. So we've talked about kinetics. We talked about reaction rates when we were doing, I think it's unit 5. We talked about enthalpy when we did unit 6. And we're going to talk more about equilibrium. Like, this takes the whole thing and brings it back together. That's why this unit's kind of cool, because it's a nice synopsis of a lot of the things that we do redox reactions in this unit. So that brings back unit 4. So it's just a nice review of all those different things. All right, enthalpy then describes the energy required or released in a chemical process. We know that exothermic processes are ones that release energy, and they are favored. So exothermic is favored. That is where your delta G is negative. Entropy is the amount of energy as a function of temperature that is not available for work. So this is energy that's tied up in some other system, okay, because it's in that molecular disorder. The things can't fit together in the same orientation. There's other things at play, little gremlins in there that are acting up and not letting the reaction happen. Yeah. That'll actually happen. As opposed to here, this is not going to happen. Okay, so this is not thermodynamically favorable. So we know from the second law of thermodynamics that an isolated system, a sample will arrive at a state of equilibrium where entropy is highest. So the processes that move to a greater entropy, or a delta S that is positive, these are favored. So that's where in this chart, if we have a negative delta H and a positive delta S, it doesn't matter what temperature this exists at, it's always going to be favored. Okay. And if we have the reverse of that, it doesn't matter what the temperature happens, it's not going to happen unless we intervene somehow, but we'll talk about that intervention later. Here, if we have this as a positive and this is a positive, it will happen if we have a higher temperature. So this is your ice melting. And then this is the negative, negative. I like to think of instead of these arrows here, I like to think of these as plus and minuses. And my brain just works better with that than trying to interpret these greater than, less than things. All right. So we got some of that stuff kind of brought in. In some cases, it's necessary to consider both enthalpy and entropy to see if it will be favored. So that's what I was saying. With the water freezing, you can look at that and determine whether it's going to happen. Okay. Likewise, if we put sodium nitrate, we know that sodium and we know that nitrate, those ions, when we place anything with those ions in it, we're going to have a dissolution. Okay. That is endothermic, so it's going to absorb heat from water. However, the ions are more disordered when they're dissolved, and so the entropy increases, and that reaction is spontaneous, or it's thermodynamically favorable. Again, they don't really like that term, so try to get away from that. You can think it in your brain, but write this on your paper. Write this on your paper when you need to. So there's lots of different factors to consider to determine if it's going to be thermodynamically favorable. First, we have our entropy. Okay, I showed you how to calculate delta S last week. When an exothermic reaction takes place, heat is transferred to the surroundings. The surroundings in turn increase in entropy due to the added energy. When the temperature is already high, there's less change in that entropy when it absorbs that heat. And when the temperature is low, there is more change in entropy. So that means that the entropy of the surroundings is proportional to the enthalpy and inversely proportional to temperature. Essentially, what they are doing is they are deriving in these steps, and if you want to go through the mathy of it, you can. They are deriving this equation. Okay? So if you want to go back, step back and at home and look through those equations up there. But essentially, the bottom line is this. Okay? When delta G is less than 0, so when delta G is negative, then it is thermodynamically favorable. One of the things that you need to be very, very careful in is that this is typically given to you in kilojoules per mole. And this guy right here is given to you in kilojoules per Kelvin mole. No, not kilojoules, my bad, joules. So you need to convert this value into kilojoules. So be very, very careful with this. This is where people oftentimes go wrong. The tables give you this in joules. This is in kilojoules. How do we convert? You just slide that decimal 3 spots over.
Do we have to do anything but the Kelvin on the bottom?
With this, it's going to cancel out with the temperature here.
Oh, okay.
So the other aspect of this equation here is temperature. And you have to have that in Kelvin. So this temperature will end up canceling out. If you have Kelvin here, and you've got this guy in joules per Kelvin mole, this Kelvin's going to cancel out. And once you convert this into kilojoules, then you can do this subtraction with this guy. Does that make sense? All right. Again, make sure you check your units because that is a very common place where people will end up getting tripped up. All right. So we know that if temperature increases, then the entropy is going to increase. Also, as an increase in temperature would magnify the entropy. It's going to magnify the entropy because the entropy is getting multiplied by the temperature here. If I can clean this up enough to see it again. I've been marking all over it, y'all. Sorry. So if we magnify this guy, if we make him bigger and we're multiplying by this, then that's going to make this bigger. Since we know that entropy is energy that is unavailable for useful work, it is the energy lost to that disorder. We're going to subtract this term from the enthalpy. And that's going to give us the energy that's available to do the work. They give you these tables. You do not memorize them. Okay? I gave you the tables back in unit 6. I want to say 6. When entropy is favored and enthalpy is favored, then the reaction will be thermodynamically favorable. And again, this is that table that I wanted you to get in your brain So we need to calculate delta G in order to determine if it's thermodynamically favorable. Right? Delta G can also be calculated. You guys have seen this equation here. Okay? It's the sum of the products minus the sum of the reactants. So if they give you the delta G values, you can get those from that. And then delta G is going to be calculated that way. All right. Decomposition of hydrogen peroxide occurs slowly at room temperature according to the following. You are going to figure out what delta G is going to be, what sign it is, and then justify your answer. It's going to happen. Do we need to intervene with any extra energy? What does it say? So if this happens without any extra energy, it's going to happen slowly, but it's going to happen without anything added in. Then the delta G is going to be what? Positive or negative? Negative. Because negative delta G, those are thermodynamically favorable. Okay? It's going to decompose without any energy being added to the system. So no new energy is added. So that is your justification. It happens slowly at room temperature. So if it happens without any intervention, adding energy into it, then that means that that is thermodynamically favorable. Don't say spontaneous. That makes them unhappy. Predict the sign for delta S and justify your answer. Well, if we are going from this to this, we've taken how many moles here? Oh, they've got this balanced up here. There we go. That's better. We've gone from how many moles here? 2. So what has happened to our delta S? It's increased, so it's become positive. We've created more moles here. All right. We do is here. I'm going to let you go home and watch the video on that one. For this guy right here? Yeah. If the thing happens on its own without any intervention, then the delta G is negative.
How do you know if it's like has something?
What?
How do you know if there's like something else?
Well, they would have had to say you had to apply electricity to it or you had to do something else to it.
Okay.
So like your batteries in your cell phone, they are thermodynamically favorable when they're making your cell phone work during the day. But to get that battery recharged, that's not thermodynamically favorable. So you have to plug it into electricity. You have to add energy into that to get that reaction to reverse. So that reverse reaction is not thermodynamically favorable. So if we wanted this to go back to hydrogen peroxide here, since this is negative, going this direction, if we wanted to go back the other direction, we're going to have to add some sort of electricity or some other energy into this to make it happen. Because the reverse reaction is always, if one is thermodynamically favorable, the reverse reaction is always thermodynamically unfavorable. All right. So I'm not going to do this. This is the same as what you've been doing for those reactions where you've had to do this guy right here. Okay, so that reaction, you've done that with delta S and you've done it with delta H before. So I'm going to skip that. You can go home and watch the video on it because we're on an advisory day and I've only got like 10 minutes left here. I want to make sure I got time. All right. If the values for Gibbs free energy is negative, that means that it is thermodynamically favorable. However, not all reactions that are thermodynamically favorable actually happen. For example, the reaction for carbon diamond to carbon graphite is thermodynamically favorable. However, we don't observe diamonds turning into graphite even over the course of thousands and thousands of years. I mean, they've got, where they go and mine these things, there's still diamonds left. My diamond on my finger here has been here for a long time. Okay. The diamond allotrope of carbon. So allotrope is just another form of it. So here is what diamond looks like. This is what graphite looks like. Graphite is in these sheets. So every time you write with your pencil, you're sloughing off some of these sheets of graphite and leaving it behind on your paper. Okay. So the allotrope of carbon has many strong covalent bonds in its network. It forms a large macrocovalent network solid. Remember, this is one. Diamond and graphite are two of your covalent network solids that I told you need to have those memorized for the year. The other ones were like silicon dioxide and silica or something. We'll go back on those. We'll get back to those later this year. But those are ones that should be kind of in your brain as a little bit of a red flag that when you see those, you're like, oh, yeah, there's something special about these. Okay. All right. So for carbon as diamond to turn into graphite, it would have to break all of these bonds here that are formed. Okay. And to break those bonds and form into a new structure would require a stupid high activation energy. So it's very unlikely that that's going to happen. Classic example here of a reaction that is thermodynamically favorable yet doesn't happen. And when we see that, when we see something that has a negative delta G and yet it still doesn't happen, we say that that is under kinetic control. Because the kinetics of that reaction, that rate, okay, is going to dominate. And that's going to prevent these things from happening as far as breaking those bonds. Generally, if the thermodynamics predict that it will happen, but it doesn't, we are going to make the assumption that that reaction is under kinetic control. And that is due to it having a high activation energy. It can't form proper orientations. It can't get the stuff lined up in such a way that it's going to happen. Remember, I talked to you about orientations. I had a pen. I brought the pen together with the lid, and I have to have that lid oriented just right and aligned just right so that I can get it back on the pen. Or there's a high number of particles that have to happen simultaneously. There's just too many things that have to get lined up that it's just not going to happen. Okay? Kind of like me winning the lottery. It's not going to happen. I can keep buying the tickets, but it's still not going to happen. All right. So consider the following. If we have this reaction here, all right, we are going from 2 moles of stuff to 3 moles of stuff. So what is my delta S? Entropy, positive, okay? What is the sign for delta H? How do you know? Nope. That's not how you know. How do you know? Ah, yes, right there. It's an exothermic reaction. So if this is an exothermic reaction, that means that our delta H is negative. When will delta G be negative? Always, never, high, or low temps. Go back to your chart. Find where this is positive and this is negative. But remember, the chart's set up so the delta H comes first. So look for your negative, positive. It is always, yes. Okay. This reaction does not proceed at room temp. Can you suggest a condition that will make this reaction proceed? Why doesn't it exist? What would we give if they asked us why it doesn't proceed, even though it is delta G is negative? What would we say? It's under kinetic control. Okay. So how do we override that kinetic control? What will we do? High temps. Yes, we are going to increase. This is at room temperature. We are going to increase the temperature. And what that's going to do is it's going to give those reactants more energy. So that is one option. So we could increase the temperature to give reactants more energy. There's one other way that we can do it. You got to kind of think back to Unit 6. I think it's Unit 6. Might be 5. What? A catalyst. Yes, we could introduce a catalyst. What does a catalyst do? All right, but why? What does it do? Yes, catalyst will lower the activation energy required for that reaction. And it oftentimes does that by making it into a two-step reaction instead of a one-step. Okay, now, should I have written these justifications down here? Did they ask for a justification? No. Then do not write that stuff. I did that so that you would understand it. But when they are asking for these, just answer the question. Don't add anything else in. Okay? You add extra stuff in and that extra stuff is wrong, they're going to mark it wrong. Even if you gave the right answer here, if your justification's wrong afterwards and they didn't ask for it, it's wrong. I would think so, yeah. All right, so now consider the reverse reaction. Okay, so we're reversing this. If that's the case, what's going to be my sign for delta S? Negative. What's going to be my sign for delta H? Positive. Will delta G be negative? Ever? Ever. No, it will never be that way. Okay. The reaction does not proceed at room temperature. Can you suggest a change to the conditions that could make this reaction proceed? Would increasing the temperature make a difference? No. Would introducing a catalyst make a difference? No. So it will not, no. So I cannot. It's not going to happen. Guess what you're doing with the we do? Yep. And you are going to do these tonight. I will see you tomorrow. Because the bell is supposed to ring at 4:44. So you got less than a minute to get packed up.